In a previous lecture we've learned that with our heliocentric model it is easier to explain the phases of the Moon as a result of the relative position of the Moon in its orbit, the Sun and the Earth. It is also easier to explain the seasons due to the tilt of Earth's axis of rotation and hence the directness of the Sun. And it is easier to explain the difference between solar and sidereal days. However, as we pointed out, the geocentric model can do all of these. In today's lecture, we will explore a few more observations that seem simpler with the heliocentric model.
Let us begin with the seasons. Again, only notice this orbit now and go to the next slide. Here it is again, the Earth's orbit around the Sun. But notice that the stars in the background, in reality incredibly far away, are either behind the Sun or opposite the Sun. Obviously you will not see the constellation Taurus in May, but you will see it opposite the Sun in November. That is, you will see it at night in November. What is your zodiac constellation? Think about that for a while. That is, in what month were you born? Well, you can't see your zodiac constellation during your month of birth. Interesting, isn't it? In next week's lab, you will hopefully see that the constellation we see at night at this time of the year are Scorpius and Sagittarius, zodiac constellations of the months of November and December. That is, the zodiac constellations that rise and set with the Sun in November and December are actually visible at night in June and July. Now try and think about which of these four answers is the correct one. Wait before you click on the next or arrow buttons. After you come up with the answer, click and the answer will be emphasized. Here is a slightly more thorough picture of the Earth, the Sun and the constellations. Note that the Earth's location is not perfectly lined up with the constellation of the zodiac of the month. It's just a little off. We will talk a little bit more about it next lecture. Again, try this question. See if you can get it before you actually click. We've seen that the positions of the constellations of the zodiac can be explained nicely with Earth's motion around the Sun. Now let's look a little closer at eclipses. When I introduced the phases of the Moon, I mentioned that we didn't have eclipses every month. Here's why. The orbit of the Moon is slightly tilted relative to the ecliptic, just about 5 degrees. It is only when the nodes line up with the Sun and the Moon that we get an eclipse. We get a solar or a lunar eclipse. You can click back and forth now. I chose a picture where the setting Sun and Saturn make the main line of the ecliptic. You can see here that the Moon and Venus in this case are slightly off from that line due to the tilt of their orbits and the fact that the picture was not taken when the Moon was at the node. Go back to the picture with the lunar orbit. That hoop on which the Moon goes is not doing a hula hoop. It remains tilted in the same general direction for almost a year. That is, the plane doesn't swivel. The plane points towards the same direction. It's not pointing towards Polaris, it's pointing towards something a little bit away from Polaris, but it is pointing towards one direction. Well, why not exactly a year? Why isn't it keeping its plane exactly for a whole year? It's doing a very slow hula hoop indeed. So why does it do a tiny little bit of a hula hoop? More on that again in a few lectures. Just another picture of the Earth and the tilted orbit of the Moon for you to see. In this picture, of course, this tilt is exaggerated. Now, talking about those nodes. When you do have the Moon, the Sun, and the Earth line up, when would you have a solar eclipse? That is, when would you have a moon that eclipses the Earth? In which phase of the moon would that be? That previous question was about a solar eclipse. Let's start with a lunar eclipse though. That is, we get a lunar eclipse exactly when the phase of the moon is the full moon, because that's when Earth is in between the Sun and the moon, and it shades the moon. As we've seen in lecture 2, the moon is seen to be eaten up, and then for about 4 hours it is much darker but tinted red-brown. A fellow by the name of Christopher Columbus used this knowledge of when there are lunar eclipses to get provisions from the king of Haiti on his third voyage when he ran out. After the natives no longer wanted to provide him with nourishment, he warned them that the anger of the moon would be upon them. Oh, but wait, Columbus was before Copernicus. How come he had predicted eclipses in his calendars? Guess what? Again, the eclipses can be explained with the geocentric model as well. Here is a better explanation for the red moon during a lunar eclipse. I understand some of you have actually seen this when it happened in April of this year. One way of telling it is that the person on the moon during a lunar eclipse will see the sunset from both sides of the Earth, actually from a ring surrounding the Earth. Go ahead and try and get this one. I'm pretty sure you will get it. This question is just a little trickier than the previous one. Now, solar eclipse is when the moon hides the sun. When that happens, areas on Earth may become completely dark, as if it was night time, and they would become completely dark at noon. Okay, the longest it would happen is for a few minutes, but indeed it does happen. Now, since at that time the moon would rise at 6 a.m. and set at 6 p.m., what is the answer to the question above? As you can see, not all of the Earth is shadowed by the moon, since the moon is smaller than the Earth. Sometimes, in eclipse season, the moon is a tad further than in other times. In such times we will only have a partial eclipse, no darkness anywhere on Earth. I like this image because it shows the region's penumbra where you would be able to see the sun eaten up by the moon but not completely cover it. and the regions where it will be totally dark.
Here are a couple pictures where the sun is eclipsed by the moon. The sun, therefore, disappears for actually up to 4 minutes. Whereas lunar eclipses take up to 4 hours, solar eclipses only last at most 4 minutes. And by the way, in 2017, in 2 years, we're going to have a solar eclipse right here in the Kansas City area. What happens during that time is that because it gets dark, birds usually get confused and begin to nest. Sunflowers close their blossom, and Chinese astronomers get beheaded. That last one is a true story. In about the 10th century AD, a few Chinese astronomers, probably relying on their understanding of half-spherical Earth, that's the way Chinese astronomers explain the size and shape of Earth, and all of the other objects orbiting Earth, with that model they were not able to predict the eclipse of the sun despite having a fairly complex model of the stars and the planets. As a result, since this was a bad omen for the Emperor of China, he decided to take revenge on those astronomers.
Here you can see where the solar eclipses paths will be on Earth in the first 25 years of this century. Notice that we will have a total eclipse near Kansas City on August 21st, 2017. Mark your calendar. This is a once-in-a-lifetime event. Also notice the interval of July 2009 to July 2010 and March 2015 to March 2016. You will note that that interval is a little less than a year. Note that during a total solar eclipse it is easy to see the sun's corona. That's something that is really hard to see when we do not have an eclipse. Therefore, we learned about the sun's corona, the sun outer layers, exactly when we observe the sun during solar eclipses.